You know, in the nuclear chart, I show all the stable nuclei. The black dots represent the stable nuclei. My goal here is to find the most stable nuclei. You know, here you have the black line, which represents the position of the most stable nuclei for each value of A. For example, here we have a line of A equals to 60. You know, it's called isobar line. Why? Because all the nuclei here have the same number or mass number A. On this line, we have one most stable nucleus. Okay, sure, it's somewhere here, for example, on the line. And for A equals to 137, one of the nuclei here, we have one most nucleus. It's on the line. Okay, and so on. We can take any value of A and we can find the most stable nucleus. How? We can find an expression of the equation of this line. You know, this line has an equation between Z and A. For each value of A, we have one value of Z. For each value of the mass number, we have the most stable, or we have the atomic number of the most stable nucleus. How can we find this relation? First of all, you know, we have the nuclear mass. Mn equals to the mass of the individual nucleons minus binding energy divided by C square. For the maximum B, I mean, in the case of the maximum binding energy, we have the minimum mass. Okay, why? Because we have a negative here. Each time we increase the quantity, the value of the binding energy, we decrease the mass. So the binding energy, the maximum binding energy of the most stable nucleus has the smallest mass. We have here a relation between the maximum binding energy and the small mass. This is the properties of the maximum of the most stable nuclei. Okay, they have maximum binding energy and small mass. So here, you know, we have calculated the binding energy by the liquid drop model. We can substitute the value of B here. We get the general relation of the semi-empirical mass formula, where we have the mass of the nucleus, we have the mass of the nucleons, and we have the value of the binding energy inside. Okay, the most stable isotope will have the smallest nuclear mass. For minimum mass energy for a given A, Z can be obtained by delta M C square divided by delta Z equals to 0. You know, we have a minimum value of M. M, it can be a constant. It must be a constant. For each value of A, we have only one minimum value. Okay, so we differentiate M in terms of Z, it must be equal to 0. Here, before, let me simplify the relation. You know, initially the asymmetric term was like this. A asymmetric n minus z square divided by a, this one. Okay, we substitute the value of n by a minus z equals to a minus z square divided by a. We get here a minus 2z, okay? A minus 2z divided by a, okay? Now, what we have to do, we put a minus 2z square equals to a square minus 4z square minus 4az. We put its value here. We get this new relation, okay? Just I want to simplify this one by putting z square, z, and a, okay, as a common factor. So here we put z square as a common factor. We put z and a, okay? We start with z square. Here we have uh, z square. So we have a coulomb divided by a power 1, 3. Here also we have z square. So we get asymmetric times 4 divided by a. Okay. We go to z as a common factor. We have here mp c square. We have minus mn c square. And here also we have z and a with a, we get only minus 4a symmetric. A. Here we have 1a, mn c square, a minus av, and also we have here a term with a. You know, a power 2 over 3 equals to a times a minus 1 over 3. Okay, if we take a common factor a, we get a surface divided by a power 1 over 3. Okay, and finally here we have a squared divided by a. We get a asymmetric. So we have asymmetric minus delta Zn. You know, here it's an expression with z square, z, and a. So the mass dependence on z at a constant value a is a parabolic curve. Okay, if we plot here m in function of z at a constant a is constant, we get a parabola. The minimum mass value, it will be for the most stable nucleus. Okay? And here we have unstable and unstable, or we can say less stable. But the most stable nuclei or nucleus has the smallest mass. Here. Okay, now we go back to the condition. We have to calculate, we have to differentiate delta m divided by delta z. Here we get 2z times this one. Okay. Here we get z mpc square minus mn c square minus 4a symmetric. And here we have a constant and constant. We can simplify this relation. You know, this value and this value is about 0.7 MeV. Okay, only asymmetric, it's about 23 MeV. So we can say these values are negligible. We can neglect these two terms. Finally, we get a simple relation between Z and A, where Z equals to 2A divided by 4 plus A coulomb divided by A symmetric times A power 2 over 3. This is the most stable, or the atomic number of the most stable nuclei for a most stable nucleus for a given number of A. For each value of A, we can calculate Z. I want to take two conditions. If you come back to the nuclear chart, for the light nuclei, in general, they have the same number of N and Z. Okay? In general, it's like this. So for a small or light nuclei, Z equals to N. Let me see here. Light nuclei, I mean we have a small value of A. For a small value of A, it means this term equal to 0. Okay? Relatively, approximately 0. So we get Z equals to 2A divided by 4 equals to A divided by 2. So A equals to 2Z. It means here N equals to Z. Okay? When A equals to 2Z, so N equals to Z. So if we have a heavy nuclei, in this case, for the heavy nuclei, N here, N is slightly greater than Z. Put here Z divided by A. We put A down here. This value is less than 0.5. In this case, we can say Z divided by A less than 0.5. So N must be greater than Z. Why? Because Z divided by Z plus N less than 0.5. So in this case, N must be greater than Z. Anyway, it's an important relation between Z and A. We have to find this relation if I ask you, or you have to know it. Okay.